Hi, this is Joe with MDPI Encyclopedia. Today we're delighted to welcome Professor Dr. Athina Meli, an editorial board member at Astronomy, to talk to us about her research on cosmic rays and high-energy astrophysics. Welcome, Professor.
Thank you very much for the invitation.
So before we begin, could you please tell us a little bit about your academic journey and tell us what inspired your focus on cosmic rays and their acceleration mechanisms in extreme environments?
Yes, my journey began with a PhD in high-energy astrophysics from the renowned Imperial College London, where I was drawn to the frontier of astroparticle physics and high-energy astrophysics, particularly the mystery of how nature accelerates particles to ultra-high energies. I was fascinated by the idea that understanding cosmic rays required bridging theoretical physics with plasma astrophysics and computational modeling. So that curiosity set the course for much of my career. So over the years, I've held positions and carried out research in institutes across Europe and the US, including Imperial College London, the Max Planck Institute for Radio Astronomy in Bonn, University of Athens, JEM University in Belgium, and most recently here in North Carolina, A&T State University as a professor of astronomy and astrophysics and planetarium coordinator. I've also been part of major cosmic ray and neutrino observatories and experiments, including IceCube, Auger, Antares, and POEMMA. These collaborations have shaped my research style, one that combines advanced computational methods like Monte Carlo, particle and cell simulations with observational insight, all aimed to reveal the complex processes that drive particle acceleration in astrophysical sources like active galactic nuclei, gamma ray bursts, and relativistic jets. So this is my main focus, and I'm excited to work with those.
Excellent, yes. And apart from those roles, you're also an editorial board member of Astronomy. So what role do you see for this journal in advancing research on high-energy astrophysics and cosmic ray studies?
My editorial vision is to cultivate the Astronomer Journal as a hub for multidisciplinary research that connects observation, simulation, and theory. The field of astrophysics and astronomy is undergoing a major transformation with multi-messenger astrophysics, which now offers simultaneous views of cosmic rays, gamma rays, neutrinos, and even gravitational waves. So I believe the journal is well positioned to amplify this integration by encouraging contributions that tackle problems across all these domains, by using modern tools from large-scale simulations to machine learning, enhanced data, and so forth. From my perspective, as someone who is embedded in global observatories and computational research, I'd like to see the journal support cross-collaborative, cross-institutional projects, particularly those that leverage hybrid methods and open science practices as well, which includes promoting reproducibility, encouraging public code releases, and generally highlighting synthetic observables from simulations, as a bridge to interpret data from the next generation telescopes and instruments.
Excellent. Yeah, so let's talk a bit more about your research in depth now. So your work explores particle acceleration in high energy sources like active galactic nuclei and gamma ray bursts. Could you explain a bit why understanding these mechanisms is crucial for modern astrophysics?
Active galactic nuclei, or AGN, are the extremely luminous cores of many galaxies, powered by supernova black holes that accrete matter and release energy across the electromagnetic spectrum. We also have gamma ray bursts, on the other hand, that are intense flares of gamma rays, and gamma rays are the most energetic form of light, which is emitted during catastrophic events, I will say, like the collapse of massive stars or neutron star mergers and so forth. Both of these phenomena often produce relativistic jets. These are narrow beams of plasma that are launched at nearly the speed of light. They are launched from close to the black hole or generally the explosion site. So the jets are crucial because they act as natural particle accelerators. They propel charged particles to energies far beyond anything we can achieve on Earth. These jets are the likely sites of where cosmic rays, including ultra high energy cosmic rays, are born. So they are very exciting sites. So by understanding the physical conditions in these jets and how the magnetic fields evolve, where shocks form or instabilities develop, we can get closer to solving long-standing puzzles, I would say, for more than 30 years now, or even 40. What powers the cosmic rays, first of all? Where do high-energy neutrinos come from that we observe all the time with our detectors? And how does the energy move from black holes into the surrounding interstellar or intergalactic medium? So these are very hot topics. In both our recent simulation-based studies, my team and I, we explore how magnetic turbulence and reconnection inside these jets can efficiently energize and accelerate particles. Our latest work traces even the resulting radiation directly, offering synthetic spectra that we can compare with real observations. The bottom line is that it's this direct link from fundamental plasma physics, electromagnetism, to observable signatures that make understanding these mechanisms very central to modern astrophysics. And this is critical because such distinctions allow us to probe the microphysics of astrophysical jets and differentiate between competing models by using real observations. So the one helps the other.
Fascinating. So these relativistic jets that you've mentioned, I think one focus of your research is the relativistic jets with helical magnetic fields. So what key insights have your simulation studies revealed about their dynamics and their role in cosmic ray acceleration?
We've used the largest scale possible, fully relativistic 3D simulations to investigate how helical magnetic fields evolve in jets, which are composed of either electron, positron, or electron ion plasmas that are found in nature in astrophysical environments. So the topology of these fields and their strength are key for stabilizing the jets and accelerating the particles within it, while they are also create conditions ripe for instabilities, which are very, very important in plasmas. They are the source of many phenomena. So what we have uncovered in a very recent study is that instabilities in the plasmas, like, for example, the Weibel or kinetic Kelvin-Helmholtz instabilities and others, they grow into the plasma as it evolves and interact in complex ways. And they produce the so-called filamentation, turbulence, and very important magnetic reconnection sites where the particles are accelerating in those sites. So the reconnection zones are very crucial for particle acceleration. So building on that, further, our very latest paper, like a few months ago, it was published a few months ago, takes one step further and calculates synthetic spectra, directly from the simulation now. And so we trace electrons that accelerated through these instabilities and find that the radiation signatures, especially in an off-axis viewing geometry, show spectral slopes that are consistent with theory following the jitter radiation, so-called jitter radiation. This suggests that in highly magnetized and turbulent regions of jets, traditional synchrotron models may not fully capture what's actually been emitted. So these insights could be crucial for interpreting the data for future missions, focusing on polarimetry and other time-resolved spectra in AGN, as I mentioned before, and gamma ray bursts.
Okay, thank you for that. So the AGN and gamma ray bursts, these are quite extreme environments and quite extreme processes. So they must be very difficult to observe. What are the main challenges in modeling and observing these processes, especially in distinguishing between different acceleration mechanisms?
Yeah, one persistent challenge is the multi-scale nature of this problem. So, see it this way, we are dealing here with microscopic plasma instabilities that evolve on the so-called skin depth scales. This is of the order of 100 meters or so, but these are embedded in jet structures. The jets are stretching across kiloparsec, meaning like thousands to million light years. So it is very important to note in that scenario that the particle in cell simulation approach is unmatched in resolving microphysics, but it is computationally demanding and limited in special extents. On the other hand, the MHD approach scales much better, but nevertheless, it lacks a kinetic detail that the particle in cell simulation approach offers. So that is why I like it more. So this is, I believe this is where hybrid approaches and collaborative modeling frameworks are in need. So we can use both methods. It will be excellent. So another challenge I find from the observational point of view is leptonic and hadronic models. For example, they can produce very similar photon spectra. And without time-resolved polarization or neutrino detections, it is very hard to distinguish them. And my experience with observatories, as I mentioned before, like IceCube and Antares, has shown that neutrinos offer a unique probe of hadronic acceleration, but the low event rates mean we need precise model-informed predictions in order to interpret them. So this is exactly what simulated led work like ours is aiming to provide, meaning to physically get grounded predictions that can guide the next steps in observational strategies.
Right. So it sounds like you need to use incredibly cutting edge technology to make these observations. So how do advances in computational simulations and multi-messenger astronomy contribute to resolving open questions in high-energy astrophysics?
There are several advancements that revolutionize the field at the moment. On the simulation front, my team and I are now able to use the detailed kinematic capabilities of particle and cell simulations to inject much more realistic, relativistic, cylindrical magnetized jets into a background plasma, trying to simulate the real world, nature, and then watch as the instabilities naturally develop and evolve into the nonlinear regime, which is very, very important to understand this phenomena. So our study results offer a self-consistent look at how plasma turbulence, reconnection, and jet composition accelerate particles and shape, at the end of the day, the observable spectra that we get with telescopes and other experiments. Multi-messenger astronomy provides the validation mechanism currently. So when a simulation predicts, for example, a burst of off-axis jitter-like radiation or neutrino emission, for example, which is tied to some magnetic reconnection site, and at the same time the observatories detect a matching signal, then we know we're getting close to the truth. So these techniques work best in tandem. So the future lies in closing the loop, I will say. So letting simulations inform observations and using observations to refine simulation inputs. So this is our goal, the final goal.
Excellent. And aside from that, what future observational or theoretical developments do you believe are most needed to deepen our understanding of the origins of cosmic rays and their propagation?
We need better composition data and more sensitive wide field observatories that are capable of catching transient accelerators in real time, I would say. So instruments like POEMMA and GRAND will hopefully give us composition tagged ultra high energy cosmic rays or neutrinos. which allows us to trace the particles back to their sources with much more confidence. In parallel, instruments with high time resolution, like gamma ray and X-ray polarimetry, will help us to determine at the same time the magnetic field geometries at the acceleration sites. So these are going to be very, very helpful for us. So theoretically, the need, I would say, is twofold. We must continue developing hybrid simulation frameworks to use, particle cell simulations and MHD approaches, so we can couple kinetic and fluid physics across scales. And I guess, and I believe we should adopt broadly highly sophisticated statistical tools like machine learning, AI, so forth. And so we want to mine the vast output that simulations will produce. With such tools, we can start to identify universal signatures of particle acceleration, magnetic topologies around jets or plasma turbulences that might be present across different classes of astrophysical sources. And we will get many answers from those.
Fascinating. So looking ahead, what emerging trends, such as new telescope facilities or simulation techniques, do you find most promising for breakthroughs in this field?
Several trends excite me. First, the rise of integrated multi-messenger campaigns, where telescopes, neutrino detectors, and gravitational wave observatories coordinate in real time. This opens the door to pinpointing the origin of ultra-high energy cosmic rays and neutrinos. Facilities like CTA, IceCube Generation 2 or IceCube Gen 2, the James Webb Telescope, Vera Rubin Telescope, the Roman Space Telescope, and the ambitious Habitable Worlds Observatory in the near future, like in the following decade or so, will play central roles in the future of astrophysics and astronomy. Second, we are entering a golden era for computational astrophysics, machine learning, AI. So in our case, for example, in my work, high-performance computing centers now can support easily 3D particle cell simulations with billions of particles, and GPU acceleration allows for longer run times and more complex physics. So in our work, we have begun, for example, incorporating synthetic radiation calculations directly into the simulation workflow. Before it was very difficult, like 5 years ago or 10 years ago. And so we close the gap between theory and observation. The next step, I believe, is real-time simulation validation, like running models in parallel with transient events and observations and adjust parameters on the fly. So it will be amazing. So that's the kind of the future I find most compelling.
Excellent. Yes, it sounds like we and the readers of astronomy have a lot to look forward to in the future.
Absolutely, yes.
Professor Meli, thank you very much for your time. It's been a pleasure talking to you.
Thank you so much.